Hi, and welcome to the second lecture of the course Machine Learning. In this video, I'm going to introduce you to a few fundamental machine learning algorithms that every machine learning expert needs to know about. Let's start with one of the most well-known machine learning algorithms, that is linear regression. Regression is a very simple concept. You want to predict one set of numbers given another set of numbers. For example, you might want to predict how long a person will live given their smoking habits. Or, for example, uh, meteorologists might want to predict the next day's temperature given the previous day's temperature. In general, we'll call the numbers that you're given to the model as the inputs and the numbers that you want to predict as the outputs. You'll sometimes hear people also refer to the inputs as predicators or or features. What makes regression different from classification is that the outputs in regressions are real numbers. In classification problems, you might use numbers as a dummy code, for example, for categorical distinctions. For example, 0 could represent healthy emails while 1 represent spam emails. But in a sense, these numbers somewhat are lacking the numberness. So the value really doesn't much anything in themselves. They are just representing something else. So as I said, in regression, the essential fact about the output is that they are real numbers. You want to predict things like temperature. Uh, for example, could be 35 degrees, I don't know, 20 degrees. And because you're predicting numbers, you want to be able to make strong statements about the relationship between the outputs and inputs. For example, you might want to say that when the number of packs of cigarettes of a person doubles, then their predicted span cuts in half. The problem, of course, is that wanting to make precise numerical prediction isn't the same thing as actually being able to make predictions. To make quantitative predictions, we need to come up with some rules that can leverage the information we have, and various regression algorithms that the statisticians have developed over many decades provide different ways to make predictions by turning input to outputs. In this video, I'm going to cover how regression model works, and specifically, I'm going to talk about linear regressions. One thing that you need to know before going to the next slide is that whenever we are doing modeling, is regression or anything else, as modelers, as scientists, as engineers, we need to make some assumptions to make our life easier. And that is valid also for making regression models. Uh, Say it in another word, we need to make some simplifying assumptions so that we could get things to work. And these assumptions will describe the underlying linear regression model. Using only linear regression is less of a restriction that you might seem. I mean, linear regression sounds very easy and very restrictive, but in reality, linear regression is used at least 90% in 90% of practical regression applications. And it could also be hacked some sense or the other to more sophisticated form of regressions with only a little bit of works. So what are the biggest assumptions we make when we're working with linear regressions? We have two major assumptions. One is separability or additivity, and the other one is monotonicity or linearity. And they may sound mouthful, but I'm going to explain them, and they're pretty easy and intuitive to comprehend. So let's start with separability and additivity. Uh, and what we mean by that is that if we are multiple pieces of information that would affect our guesses, We produce our guesses by adding up the effect of each piece of information, as if each of the piece of information were being used in isolation. And I'm going to give you an example here. For example, if we know that alcoholics live 1 year less than non-alcoholics, and we also know that smokers, I don't know, for example, live 5 years less than non-smokers, then an alcoholic who is also a smoker, and think in the context of linear regression, of course, as again, then an alcoholic who is also a smoker should live less than 1 + 5 years than normal healthy people who are not smoking, who are not using alcohol, I mean, who are not alcoholics. So in theory, they should live at least 6 years less than a non-alcoholic, non-smoker person. The assumption that the effects of things in isolations adds up when they happen together, of course, is a very big assumption, but it's a good starting point for lots of applications of regression. And we will later talk about in future lectures about the idea of interaction, which is also a technique for working around the separability assumption in linear regression. For example, you know that the effect of excessive drinking is much worse if you also smoke, so it's not that straightforward. But for now, we make this assumption. Separability, additivity are the assumptions that we make. We treat things as they were working in isolation, we just add them up together. So the other assumption when we are making when we are dealing with linear regression is monotonicity or linearity. They are a bit different. They're not exactly the same thing, but I'm going to say about that. And we say a model is monotonic when changing one of the input always makes the predicted output go up or go down. For example, if you're predicting the weights using heights as an input of your model, then your model is monotonic because you're assuming that every time somebody's height increases, your prediction of the weight will also go up. And monotonicity is also a strong assumption, similar to separability, uh, because you can imagine lots of examples where the output goes up for a bit with an input and then it starts to go down. But the monotonicity assumption is actually much less strong than the full assumption of linear regression algorithm, which is called linearity. Linearity is a technical term with a very simple meaning. If you graph the inputs and outputs of a scatter plot, you should see a line that relates the inputs to output, not something with a more complicated shape as you see here, uh, such a curve or wave. I mean, what we have in this picture here is a monotone graph. I mean, the value of the height that you don't see it in this slide, unfortunately, goes up, then the weight goes up. But it is not going up on a straight line. It's going up somewhat on a curve, which is a realistic thing. But linearity assumption, if you're to make that, is that it should go on a very straight line without any outliers outside the line. So as you see, linearity is much more stricter than monotonicity. Every linear model is monotonic, but curves, as you see here, could be monotonic but not linear. And as I said, for that reason, linearity is more restrictive than monotonicity. Okay, now let's get to some bit of theory. It's not anything complicated. I say theory whenever I use some formulas or some letters. So this is not really deep theory. It's a bit of theory. So in linear regression, we have a collection of labels examples x, I, y, I from 1 to n. It is, of course, supervised learning, so you have seen this in the previous lecture as well. And xi is the d-dimensional feature vector of examples I from 1 to n. And yi is a real value target. And every feature xj is also a real number. And what we want to do here is basically we want to build a model f of w and b of x and as a linear combination of features of our examples. So as you see here, basically the input feature is x, and the feature vector is x, and then we make a linear relationship here. So f of w and b of x is equal to wx plus b. And as you see, we have two parameters here, w and x and b, and this is why we say the model is parameterized by two parameters. And w is a d-dimensional vector of parameters, and b is a real number. What you should note is that when we have two different pairs of parameters, basically, if we have two models parameterized by two different pairs of w and b, then very likely they will produce two different models. So these numbers are important. Uh, and the question is, what are the optimal values of w and b so that we could get closest fit to the reality? Uh, in the other words, what are the optimal w and b and how we can find them so that we could predict as accurate as possible? And one thing that I should mention also here is that we call W weight and B residual. You're going to see that terms later in many different algorithms. So these are some useful terms to keep in mind. Okay, so let's have a look at this figure. It displays a regression line. The red line that you are seeing here is the regression line for one-dimensional examples, which are our blue dots. Basically, the idea is here is to find the linear regression of these blue dots, and this red line is the one that predicts the target value. We can use this line to predict the value of the target y for the unseen y. So basically, if we have this model and we are given a new unseen input value, then we can predict what the y value or the target value of the new unlabeled input example is. And if our examples are d-dimensional feature vectors, this is only one-dimensional here. The only difference with this case that you are seeing here is that the regression model is not a line, but a plane, for example, for 2 dimensions, or a hyperplane for the dimensions of more than 2. Now you see what's essential to have the requirement that the regression hyperplane lies as close to the training example as possible. It is very obvious from this figure, sorry. If the red line in figure was far from the blue dots, then the prediction of new y's would have fewer chances to be correct. So this is more of a theory, so it's a bit of formula we have here. Basically, the question we asked in a couple of slides back was that what are the optimal values of W and B? We're going to discuss that a bit more, that question a bit more. What do we say when we say what are the optimal value of W and B, and how we make sure that we have good candidates? So optimal values for W and B tries to minimize this expression that you see here. And if you try to forget about the letters that see could be scary, basically what it is happening here is this is the error value, squared, summed, and then averaged, and we try to minimize this. And this is called a loss function. The value inside this sigma is called a loss function. It is a measure of penalty for misclassification of example I. So this is basically the predicted value for example I, and this is the real value of example I. Then we subtract the real value from the predicted value, and then we square it. So somehow it is telling us how far or how close we are to the predicted value, and it is the penalty for misclassification of this specific example I. All model-based learning algorithms have a loss function, And what we do to find the best model is basically to try to minimize the objective known as the cost function. And the cost function is the whole thing here, basically. This is what I wanted to say, that this specific loss function is also called the squared error loss. The average loss or empirical loss for a model is the average of all penalties obtained by applying the model to the training data, and this is what we're doing here. So we defined a loss function here. We talked about the cost function here. There's some questions uh, coming to mind when we are doing it. We're proposing something like this. The question could be, why is the loss in linear regression quadratic function? Why couldn't we get the absolute value of the difference between the true target yi and the predicted value, and then use that as a penalty? The truth is, we could. Moreover, we could also, for example, use a cube instead of a square. And then this is where I think you start realizing how many decisions we are making where we are designing a machine learning algorithm. uh, the first one was that we decided to use linear combination of feature to predict the target. We picked our model. That was one decision we made. Then we and remember that we could also have used, I don't know, a square or some other polynomial combinations of features. But this is what we chose. We chose to do it linearly. We could also use some other loss functions that make sense. For example, the absolute difference between f of xi, which is the predicted value, and the real value makes sense. The cube of that difference also makes sense. Uh, the binary loss, for example, 1 when predicted value and the real value are different, and 0 when they are the same, also makes sense, right? So there are several different decisions that we can make. If we made different decisions about the form of the model, the form of the loss function, and about the choice of the algorithm that minimizes the average loss to find the best values of the parameter, we would end up somewhat inventing a different learning algorithm. Sounds easy, right? However, do not really rush into inventing new learning algorithms. The fact is that uh, it is the fact that it is different doesn't mean that it will work better in practice. People normally invent new algorithms, learning algorithms, for one or two main reasons. And the reasons you're seeing on the screen. The new algorithm either solves a specific practical problem better than the existing one, or the new algorithm has better theoretical guarantees on the quality of the model it produces. One practical justification of the choice of the linear form of the model is that it is simple. This is probably the main reason that people go for linear regression. This is quite simple. Why we need to use a complex model when we can use a simple one if it works? So it is a good thing to keep in mind that you shouldn't necessarily go for the most complicated approach. Sometimes easy the answer. At the same time, there's another consideration. And that consideration is that linear models rarely overfit. Overfitting is something that we haven't discussed yet, and we're going to discuss in this course. But if I want to say briefly what that is that overfitting is the property of a model such that the model predicts very well the labels of the examples. I mean, it could predict all of them correctly, but uh, then when new values are introduced, it works dramatically bad. So we talk about more overfitting more in future and how to avoid it. But for now, let's keep uh, uh, to our discussion here. So from what I said, now you know why linear regressions could be useful, and the answer is that because they don't overfit much. But what about the squared loss? Why did we make that choice? Well, uh, this is kind of historical. Several centuries ago, a French mathematician first published the sum of squares method, and And the reason was that it was convenient. And why did he do that? Because, to be honest, the absolute values are not always convenient, because they don't have a continuous derivative, and then the function is not smooth. So this is getting very mathematical, so I can probably skip that for now. But basically, closed form solutions to finding an optimum of a function are simple algebraic expressions, and often preferable to using complex numerical optimization methods such as gradient descents. And this is what we're going to discuss later in today's lecture in another video. So again, here the simplicity is the king, so that is why we are going with that. And intuitively, squared penalties are also advantageous because they exaggerate the difference between the true target and the predicted one according to the value of this difference. I mean, we could also use the powers of 3, 4, but then uh, when we are working with theory, and this is probably something you don't really see that much, uh, we use derivatives a lot, but when the power goes up, then having the derivatives becomes more complicated. So that is why we settle for a squared root, for a squared values. Okay, now we know some stuff about linear regression at the moment. What is it? How does it work? How do we perform, evaluate, how we calculate the error and all sort of thing. Let's switch to a bit of hands-on practice and see how coding looks like when we're dealing with linear regression models. Okay, so now we want to give it a try and see how we can work with linear regression in Python. This is a simple example, and it's from the dataset that is already available in scikit-learn. What we do first, we are importing some standard libraries, like as we always do, NumPy, Matplotlib, Pandas, Seaborn. These are basically for working with the data frame and doing some visualization. And from the scikit-learn package, we import linear regression because this is what we're doing here, and also the Boston dataset. So let's load our dataset first, and okay, it's done. And now let's see what are the features. We have, these are the keys: data, target, feature names, DESCR, and file name. And these are the explanation. Data contains the information for various houses, target, pieces of, prices of the house, feature name, name of the feature, and then there's also a description of the data set. So let's see what is the description of the data set. It doesn't look very nice, but I have cleaned it up for you. And these are the features that we have. We have per capita crime rate by town. We have proportion of residential land zoned for lots over 25,000 square feet, and proportion of non-retail business acres per town. Several different things. And what we are interested in is as our output is the median value of owner occupied homes in thousands of dollars. So this is what we're going to predict. So how we are going to do that? Let's see what do we have in our data set first. So this is the first 5 rows of our data set. As you see, the features are here, and let's put what we decided to be our target, this median value of owner occupied homes. And just let's, for the fun of it, check if there is any missing value, which is not. And then a bit of visualization to see if our data, it's a bit too big for you. If our data is normally distributed, it is more or less, so we can accept it as a good data set. And then what I'm going to do that is that I'm going to build a correlation matrix, because I want to see what are the features with the highest correlation with my output. Okay, as you can see, there are, where is this med? Yes, this one. For example, this LStat is a very high, of course, negative correlation with the median value. It goes up, the other one goes down. What else we can have? We can also have a look at this median value and RM. Yeah, so let's pick these two. Okay, and I have plotted basically them against the median value. You see there is a linear relationship, I mean somewhat specifically here, but here as well. And if you remember, we talked about monotonicity. This is monotone, this is also monotone, but they are not linear, but we are still using linear regression here. Okay, so let's see, let's continue with our modeling. And what I'm going to do now here is I'm going to split my data to training and testing data set. What you should know is that when we are building a model, we train our model in a portion of the data, normally the larger portion of the data, and then we test on the testing data whether it is good or not. This is something that we're going to discuss more during the course, but keep in mind, when we are doing modeling, we want to validate, we want to evaluate the performance of our model, so we need to keep a bit of data as a test data set. And what I have done here is basically I used 80% of the data as my training data set and the rest 20% for testing data set. Okay, so this is the shape of my data basically right now. So I have 404 examples in the training data set and 102 in the testing data set. And this is easy now. Basically, we are going to call the linear regression model, the import linear regression model from the linear model packet, linear model of a scale-learn, and we also import the error value that we are interested in, which is mean squared root error here. And I basically initialize my model saying that linear regression is my model. And then I'm using the training data set, X train, Y train, and I fit my model, and that's as easy as that. So it is done now. Something that you need to keep in mind is that for this specific problem that we're solving here, I have already picked two different features that I thought could be linearly related with my output value. So the model will be something like that. Y hat is equal to B0, this is a residual, B1x1 and B2x2 plus epsilon. And let's see what is the intercept here. Intercept is this B0 or our residual, and we can also see the W values, which are the coefficients for B1 and B2. So this is our W, this array is our W. So these are the things that you can find out when you're doing the modeling with these commands. I don't say specifically they mean much, or you necessarily need to know them, but if you want to know, here it is. Okay, and that one, I really didn't need that. And now I'm going to build the prediction. I built my model, which called lean model here, as you see. And then I want to predict the values of each test. You remember we put aside a portion of the data set for testing, and this is what I'm going to do here, and the rest of it really here is how we want to show that. Yeah. is for visualization. So this is the line that my model is predicting, and this is the data basically that we have. Predicted value versus true value. If everything was on this line, it was like linear, it was a perfect model, which was, then I could have said it's overfitted, but this looks good enough. But let's also do the model evaluation, and I'm going to get a value here. It's basically I'm going to get RMSE and R2, but then I explain again what does that actually mean when we go back to our slides. But this is for you to know how to use this. So you use the model evaluation both for training data set, for testing data set. You do the prediction on the training data set. You calculate these error values, the performance values, and then the same for testing data set. And let's see what do we have here. Well, this is our RMSE is this much, R2 square is this much. At the moment doesn't mean much for you. You can't say whether it's good or not, but I'm going to explain it again, and then you will realize whether we had a good model or not. Okay, now let's talk more carefully about how well we are doing the linear regression. Having the residuals is great, of course, but there are so many of them that they can be overwhelming to work with. We'd like a single number to summarize the quality of our results. The simplest measurement of error is, of course, take all the residual, square them to get the squared error of our model, then sum them together. And this is the first one, the sum of squared errors. But there are things in this simple sum of squared errors that are not necessarily good. First of all, this simple sum of squared error quantity is useful for comparing different models, but it has some issues that most people end up disliking it. First of all, the sum of squared error is larger for big data sets than for a small data set. And to convince yourself of this, imagine a fixed data set and the sum of a squares root for that data set. Now add one more data point that isn't predicted perfectly. This new data point has to push the sum of a squared error up, because adding a number to the previous sum is make the sum larger. But there is a simple way to solve that problem, and that is take the mean of the squared errors rather than the sum, and that is give us the second model evaluation matrix. We call it also MSE. And of course, MSE won't grow consistently as we get more data, the way that the raw sum of squares rule will, but it also has its own problem. If the average prediction is only off by 5, for example, and then the mean squared error will be 25, that's because we are squaring the errors before taking their mean. The solution to this problem of a scale is trivial. We take the square root of the mean a squared root to get the root mean square error, and that is called RMSE, which is very popular measure of performance for assessing machine learning algorithms. Of course, it also is used for far more sophisticated algorithms than linear regressions, for example, neural networks. One complaint that people have with RMSE is that it's not immediately clear what mediocre performance is. So is it good or bad? Perfect performance clearly gives you a value of 0 RMSE, but the pursuit of the perfection is not actually a realistic goal in these tasks, and it's not equally easy to recognize when the model is performing poorly. This unbounded value that RMSE can take, it can be anything really, make it difficult to know whether the model performance is reasonable or not. And it brings us to the solution to the problem is basically to use the R squared. The idea of R squared is to see how much better your model does than we do it if we were just using the mean. To make it easy to interpret, R squared will always be between 0 and 1, and if you are doing no better than the mean, then it will be 0, and if you predict every data point perfectly, r squared will be 1. And because r squared is always between 0 and 1, people tend to multiply it by 100 and say that is the percent of the variance in the data explained with the model. This is a handy way to build an intuition for how accurate a model is, even in a new domain where you don't have any experience beyond the standard values RMSE. To calculate R squared, you need to compute the RMSE for a model that uses only the mean output to make the predictions for all your example data. Then you need to compute the RMSE of your model. And let's get back to the model performance that we had here. As I was just saying, the RMSE really doesn't tell much, but our R squared score is 4 above 0, which is telling you is working better than average. So this is a pretty good, but still not perfect model. But this is how you could interpret it. Of course, I said how all these things are calculated, but at the end, if you're only using these measures to evaluate your model, probably you don't need that much to know what are the intricacies. That doesn't mean that this is not required for the course. This is part of the course, but in real life, in future, the important thing is to know what are the metrics that you need to use to evaluate the performance of your model. Okay, and this was it with linear regression. In next video, I'm going to talk about logistic regression a bit. See you soon.